My pit crew does a heck of a job under pressure, but it's our engineers that get the credit for making it possible. It takes just about 12 seconds to refuel my car. The designers were told to do whatever was necessary to the car's design so that all tires could be changed during that same 12 seconds. The important point here is that the short refueling time was the criteria, not the other way around. The engineers came up with this nifty pneumatic system. The first guys over the wall have the fuel line and the air hose. They are connected simultaneously as the rest of the crew with the tires and tools change all 4 tires if necessary. In 12 seconds, I'm on my way. The whole system, including activators and hoses, weighs just 15 pounds. Because this capability was designed into the car from the very beginning, the finished car weighs no more than one without it. Had the engineers not had this foresightedness and tried to add onto the system, we would have been faced with the dilemma of trading speed and performance with pit turnaround time. Our engineers know that pit time must, as we say it, match the pace of the race. It could mean the difference between winning or losing.
It seems to me that there's got to be some way to reduce the ground time required to service and repair our aircraft. In a wartime scenario, we're going to be needed in the air, not on the ground. Also, I know as well as you that with the technical advances in target detection and guided munitions, every minute we're on the ground, we're going to be extremely vulnerable. Too bad we can't design our weapon systems with some of the engineering advances those Indy cars have. Not only are they fast around the track, but also on the pits. They can usually get in and out in around 12 seconds. Did you see those internal jacks some of the cars use for tire changes? How ingenious, and what a super idea. Why can't we communicate to our aircraft designers to follow that lead and engineer the same kind of technologies into our aircraft to get us out of the pits faster? We've got a heck of a lot more to lose than a race.
The Major's question is a good one. In fact, he focuses on something that is of major importance to those of us who are charged with acquiring the Air Force's new weapon systems, something we call availability, which means taking into consideration the various factors that determine whether a weapon system is ready to go when a combat commander needs it. Availability consists of a range of factors, things like weapon system reliability and maintainability, or whether it is supported properly by sufficient spares and maintenance equipment. These are vital considerations. It makes no sense at all for us to deploy and build highly capable weapon systems if a combat commander can't rely on them because maintenance requirements are too complicated and too frequent, or the required spares haven't been bought, or support equipment has not been deployed. Over the years, we've worked hard to ensure that our Air Force bases around the world have all the services necessary to keep our aircraft flying. This approach minimized the amount of stateside logistics center support required to maintain readiness and sustain combat operations. It also assumed that our air bases would be free from attack. Today, this is no longer the case. We cannot expect our air bases to be sanctuaries. And in light of this, we must place increased emphasis on the availability factors. We must now institutionalize this emphasis and ensure that we pay as much attention to how available a new weapon system is as we do to how fast it flies, how much it carries, or how much it costs. To accomplish this, our design and research engineers have to find better ways to integrate readiness and sustainability considerations, the essence of availability, into all phases of research, development, and design. Essentially, we are calling for a new dimension of design.
As a major user of the weapon systems that you've been asked to design, I'd like to comment on some feelings I have regarding traditional logistic support concepts. We're going to have to change our support concepts to meet future requirements for air power and its application in the theater of war. Air power in the future is going to be measured by our ability to produce sorties and to deliver ordnance where it's needed, when it's needed, and for the length of time it's required, whether in the cold of a German winter or in the heat of a Middle East summer. Also, if you add the potential for nuclear, biological, and chemical warfare, you begin to realize some of the problems we face, not just for the pilots in this airplane, but also for the maintenance crews. Now, to survive this threat, we are trying to harden our facilities. It's going to take a lot more hardening before we're going to be in a posture where we can adequately perform our wartime mission. Until we get that posture, we need your help. You need to be thinking about designing weapon systems that don't require intermediate level support. Of course, what I'm talking about is 2 levels of maintenance. We need the quality and the reliability in components and a reduced unit cost that will allow us to remove and replace on the flight line and remove all these people and this expensive equipment that's exposed to the hazards of war. We no longer have the luxury of living with extended sortie turnaround times or generation times. We're going to have to turn airplanes rapidly, and we can only do that if we can reduce the need for maintenance. What you have to do is give us systems with an MTBF that is sufficient that we can look to eliminate the need for intermediate level maintenance. I'll give you an example. For a squadron of F-15s, a slight increase in MTBF would allow us a reduction of 50 people and maybe $15 million worth of avionics intermediate station equipment. This means you can reduce the lift requirement by 4 C-141 loads. In deploying a squadron of F-15s, it would no longer require the hardened, environmentally controlled facilities that we need for the AIS. The impact is simple. It means fewer people and less equipment exposed to the hazardous environment of war. At the same time, we ought to be able to dramatically increase the number of sorties we produce. So we're looking to you for increased reliability in our weapon systems, which will enhance our ability to maintain and produce an effective air power.
As General Minter points out, effectiveness of the fighting force is the bottom line. It is our goal in the development and acquisition of weapon systems, and effectiveness is the result of 2 things: the actual capabilities of the weapon and its availability. While capability is a fairly obvious requirement, the factors of availability are less well known, and only in recent years have they received as much attention as capability. Included within availability are supportability, reliability, maintainability, flexibility, and serviceability, just to name a few. These are the elements that actually determine just how good our new weapon systems are as warfighting tools. Although we've always considered these principles in the design process, the future dictates that we pay greater attention to them. In looking toward the future, we see the need for greater and greater capability in our weapons. We will be applying modern, high technology to our new systems to assure their qualitative superiority. The same kind of advanced technology must be used to improve the availability of those weapons as well. That is, the sophisticated methods available to design engineers will be used to make maintenance and support requirements simple, effective, and infrequent. Our challenge, you see, is to ensure that the weapons we build are not only capable, but that they are designed so they can be maintained by Air Force men and women assigned to that task. Further, they must be supported from the very first day they enter the inventory. We cannot afford downtimes, times when the U.S. defense establishment is at less than its peak of readiness because spare parts haven't been bought yet, or maintenance people haven't been trained, or support equipment hasn't been purchased. With increased attention to the availability factors early in the design phase, we can reduce support requirements to an absolute minimum.
You know, I see our future support requirements have to be aimed at reducing the support structure vulnerability. It's got to focus on the required characteristics of mobility and flexibility and survivability, and we just have to streamline the operational support processes through the emphasis on reliability. For example, unlike the Indy 500 race car you saw, we really don't need built-in jacks for our fighters. What we really need
are aircraft components that are durable and reliable. In short, we need to dramatically reduce the frequency of component replacement and servicing. In my opinion, technology is the way to go, and the design application that you make to obtain greater reliability and the ease of maintainability will give us less dependency on all these people in this ground support equipment, and it's essential if we're going to integrate and enhance weapon system employment and operational support. Remember, all these issues have got to be fully understood and implemented by you now.
For the future, we are going to insist on supported weapon systems. We are going to design, engineer, and build weapons that fail infrequently, and when they do, they can be repaired quickly and easily. We will ensure that when we turn a weapon system over to the user, it is ready to go, supported from the outset. Our challenge in the R&D and acquisition communities is to design and deliver supported weapon systems, systems that meet the combat commander's requirements for capable and available weapon systems. And we're going to meet that challenge.
What you have seen so far can be focused into a number of objectives. However, the major one is to develop weapon systems that are independent of a manpower-intensive unit maintenance concept, independent of maintenance facilities co-located with those weapon systems, and independent of sophisticated support systems. To achieve this independence, we need to explore opportunities to reduce current requirements for unit-level component repair. Also, we need to design future weapon systems to reduce and possibly eliminate the need for complex, sophisticated, manpower-intensive support equipment. And finally, we need to develop the rear area repair capabilities necessary to support this maintenance concept. We need to find a way to make technology transparent to the 19-year-old in some unknown backwater of the world. Now let's take a moment and look at a few encouraging examples of how the Air Force laboratories have and are attempting to achieve this objective.
Here at the Air Force Wright Aeronautical Laboratories, we are advancing technologies to attack the traditional problems in supportability. This shift in emphasis was brought about by the driving need to survive on the future battlefield. For example, we have successfully established the necessary structural and manufacturing technologies to demonstrate the integrity, reducibility, and reliability of cast aluminum primary aircraft structures. The YC-14 provided the opportunity to prove the point. The original design of this YC-14 nosebody landing gear support bulkhead consisted of 400 parts held together by 3,000 fasteners. Obviously, manufacture and maintenance would have been costly and labor-intensive. In conjunction with various contractors, a one-piece cast bulkhead was designed, cast, and tested. Although the C-14 program didn't reach production, we demonstrated a new technology that produced a high-quality replacement part at a cost reduction of 38%. Since the majority of cracks in primary structures originate at fastener holes, the elimination of 3,000 of them greatly improved the corrosion resistance and damage tolerance of this part. We are also developing a multifunctional integrated power unit, or MIPU, designed to reduce aircraft operational dependence on ground support equipment by providing power for autonomous ground start, checkout, and maintenance. It will also provide power for in-flight engine restart by utilizing a stored fuel source to assure adequate power output regardless of temperature or altitude. The MIPU will be capable of replacing both auxiliary power units with a single unit having the same weight and volume. The result will be a major reduction in ground support equipment equal to 2 C-141s in a fighter wing deployment. Another program is developing key technologies for the next generation airborne radars. Very high-speed integrated circuits, or VISIC technology, will enable us to build a programmable radar signal processor with tremendous reductions in parts, power, size, and weight compared to the current item. This VISIC chip, with its increased computational power, provides an opportunity for greatly improved built-in test, fault tolerance, and fault isolation. For example, 41 of these chips, represented by this demonstration board, will replace the entire signal processor. We estimate the mean time between failure of the VISIC signal processor at 10,000 hours. In addition, active array technology will allow us to combine the functions of the antenna and receiver transmitter into an array of these modules, eliminating some of the single points of failure. Each module in this electronically scanned array is a receiver transmitter. Thus, the antenna drive, gimbals, and slip rings are not required, and the radar will remain operational with up to 10% of the 2,000 modules inoperative. These technologies will help drive the overall ultra-reliable radar system, which encompasses fault-tolerant and fault isolation concepts, hardware and software modularity for flexibility and easier maintenance. The reliability of the total system is 400 to 700 hours mean time between failures. This is a 10-fold increase over our current baseline system. This, with other reliability improvements, will delete the need for an avionics intermediate shop. Thus, a fighter wing deployment would require 6 fewer C-141 sorties. Lastly, we have been instrumental in developing new techniques in aircraft battle damage repair. With the advanced technologies used in current and future design systems, such as composite materials, fly-by-wire control, and fiber optics, rapid repair is imperative because of our conviction that one more sortie can make the difference in the outcome of an ongoing battle. Our major effort in this area is the Aircraft Battle Damage Repair Design Handbook, which will be used in the design or modification of aircraft to enhance damage tolerance and repairability under wartime conditions. It will provide information on various design concepts, their benefits and limitations, and how to select, apply, and test available concepts. For example, this original aluminum throttle bell crank from an A4E was notch sensitive, had statically determined load paths and a vulnerable area of 8 square inches. Using the battle damage repair design concept, it has been redesigned. It's made from fiberglass, is less notch sensitive, and has redundant internal load paths and has half the vulnerable area. In the future, design goals must incorporate aircraft battle damage repair techniques as part of the survivability concept. The thrust of long-range research and development efforts must include rapid battle damage repair as a factor in aircraft design. The philosophy at AFWAL is that supportability can and must be advanced through a mature technology base and design decisions made with supportability on an equal basis with performance, early in the development and acquisition phases. These requirements must be built in at the design stage of the acquisition process, where they are most affordable.
That model is not a next-generation milk container truck. It happens to be one of RADC's major advanced development programs. We call it the Advanced Tactical Radar, ATR for short. It is the GCI radar of the future. Performance-wise, it'll be great. 1,000 track capability, 3 times the current capabilities in jamming versus the current system. But most important, it is survivable. It is designed to be set up or torn down and moved in minutes instead of the hours that it takes us to do the current system. We do this with only a crew of 3. Therefore, we don't need a large, immobile logistics tail out in the field. I felt this was an opportune program to try out a new idea, i.e., build in logistics considerations during an advanced development program. My engineers and resident loggee did not have the wherewithal to crank supportability into the program, but they sure had the motivation to seek out expert assistance, and that's exactly what they did. We came up with a supportability package that builds into the ATR 21st century logistics considerations. For instance, fail soft. I don't want subsystem failures to precipitate total ATR failure. Another consideration, built-in fault detection. Remember, I told you that the ATR is to be operated and cared for by a crew of 3, which, by the way, is a quantum decrease in crew size from the current system. They'll wear fatigues, not white lab coats, so built-in fault detection is a must. Elimination of paper tech orders is another consideration. We can't afford to drag along excess paper baggage out in the field. Those instructions have to be electronically available. Now, you've all heard of such logistics considerations before, but never has it been tried in an advanced development program. I'm a firm believer in building in logistics at the real front end. It's too hard and too costly to do it downstream. Our contractors are enthusiastic about building logistics supportability into the advanced development program. I hope that enthusiasm will spread throughout the rest of industry.
The Human Resources Laboratory is advancing technology in logistics and human factors engineering. We are now using computers to avoid maintainability problems in future weapon system design. For example, in one of our current aircraft, there's a problem obtaining an oil sample in a wartime nuclear, biological, chemical environment. There are a large number of fasteners on the oil service panel, which slows down this critical task. In addition, the panel is not readily accessible to a standing technician. Once the panel door is opened, taking the oil sample is further complicated by the bulkiness of the gloves. In an effort to solve this supportability problem in aircraft of the 21st century, we, in conjunction with the Aerospace Medical Research Laboratory, are adapting the computerized biomechanical man currently used in cruise station design. By analyzing combat-critical tasks, we will be able to ensure during the design stage that maintenance technicians in all environments will be able to rapidly maintain future weapon systems.
Thus far, you've seen some examples of work in progress. Now let's take a look at a completed in-the-field DoD example. And it's appropriate that we start this story here in the Air Force Museum with the H-5 helicopter. This helicopter was extensively used during the Korean conflict and was an excellent example of helicopter technology during its time. However, it required extensive maintenance, and especially engine maintenance, to keep it flying. Most, if not all, helicopters since then have suffered similar problems. Today, however, engine maintenance has been dramatically cut with the introduction of the T-700 engine in the Black Hawk helicopter. The Army spent a lot of time developing reliability and maintainability requirements for its next-generation helicopters to replace their Hueys and Cobras. Please keep in mind that these were hard requirements, not objectives or goals, and were so stated in the contractual documents. In my mind, these requirements represented a premeditated, planned, and logical devastation of their traditional support structure and processes. What I'm going to show you now is not pie in the sky, not ideas on paper, but a live in-being example of what a service and contractor can achieve if they both clearly understand the requirements and commit themselves to achieving those requirements. The first example is, to me, the most dramatic. These 10 common tools are all that are required to take the engine completely apart in the field and put it back together. That's right, 10 common tools. There are no special tools required. The engine requires no oil changes and no oil sampling whatsoever. Every single LRU in the engine can be changed in 20 minutes or less by one man. No operational checks, trim, or rigging is required. There is no safety wire required anywhere in this engine. Through design of an integral particle separator and more damage-tolerant blade design, this engine is literally immune to ground foreign object damage. Human engineering was an integral part of the design also. All electrical connectors are Murphy-proof. You can't connect them wrong. All LRUs and modules have self-aligning features. Most LRUs are installed using exactly the same nut and bolt. When we look inside the engine, we see even greater reliability features, such as the combustor. The original design had a life of around 1,200 hours and required maintenance about 600 hours. It was an assembled part. The new machine ring combustor has a design life of 5,000 hours, and to date, after 250,000 operating hours, not one has been replaced. What does this mean? It means a 14-to-1 reduction in maintenance man-hours per engine operating hour. I was recently told by Army development people and an E-5 T-700 engine mechanic that the biggest problem facing engine mechanics in the field today is that they are losing proficiency on the engine because it doesn't break. I'm sure General Minter would love to grapple with this kind of problem today. What is important to you is that our past traditional problems have been well defined
and engineered out of the equation by you, the design engineer.
What you have just seen are examples of how you can turn your engineering know-how and creativity into a real, supportable frontline combat capability. In effect, a new way of thinking, of designing in up front the kind of supportability and maintainability our systems must have to perform their combat mission. The era of using and then replacing after a short lifespan thousands of bombers and fighters is over. In fact, technological complexity, long lead times, and rising costs have already invalidated the concept of a firm design life. When we look ahead a few years, when we look at the millions of dollars invested in each B-1B, it's hard to believe that many of us will ever live to see the day when these airplanes are retired from the inventory. This, combined with the fact that few weapon systems live up to their original expectations of supportability and maintainability, makes one thing very clear. Logistics is, and will continue to be, the long pole in the tent. That's why logistics is the biggest business the Air Force has. That's why last year alone, AFLC employed over 92,000 people and managed about $40 billion, accounting for almost 39% of the total Air Force budget. Considering the expense and effort modern logistics demands, it only makes good sense that we find ways to design more reliable, maintainable systems from the very start. For every penny spent making up for design deficiencies is a penny less we can spend for our national defense. Clearly, the need for change is great, and just as clearly, you're the key to our making these changes, to getting where we need to be. As you look around at the large, highly industrialized, and relatively immobile support structures we presently have, it's important to realize that what you're looking at is the manifestation of failure, of our failure to design in the kind of supportability we need. In effect, you're looking at the support dependence of current weapon systems, a dependence which increases vulnerability and life cycle costs. In the final analysis, this decreases the overall effectiveness of our fighting forces. You, the engineers working in design, hold the key to success in our efforts to reduce and, if possible, eliminate this dependency. I challenge you to work together in R&D and IR&D so that we can better meet the defense needs of our country in the future.
We Americans have an innovative and competitive spirit.
We constantly seek to excel. We know that to win, we must constantly improve, be innovative in finding that elusive new and better way that will stand up to the test.
For the engineers, success is proven here, as always, in competitive performance.
In our world, the engineer's success will be judged here, in the area of supportability. It is vital to the mission of the United States Air Force and the defense of our country. You can make the difference. No, you must make the difference.